Hello everyone, welcome to Geography 113, Data Acquisition and Management here at Pasadena City College, one of our courses in the GIS certificate we offer. In this lecture, I'm going to focus on map projections, coordinate systems, and datums as part of our module on the subject. As you will have noticed, maps have different shapes and the continents often also look differently. One of these issues has to do with projections. Since all maps are projections, since all map projections are mathematical approximations, we have to remember that maps are also approximations of reality. So all maps that are projected are distorted. They have a distortion of some sort because we are trying to turn a three-dimensional object into a two-dimensional surface of sorts. So as a map maker, your job is to choose a projection that relegates those distortions to places on the map that are not important for your message. One of the ways to look at projections is also by understanding the issue of scale. So for example, here we have two maps, one on the left and one on the right. The map on the right, we would refer to this as a small scale map. The reason that we refer to it as a small scale is because we get a smaller fraction. For example, we could say that the map below is a 1 to 250,000. Most likely this will be like a 1 to several million, for example, because we're looking at the whole country of Mexico. But the fraction is smaller if we compare it to the fraction on the right, in which we are focusing on a neighborhood in Mexico City, and that is a scale, a fraction of 1 to 5,000. Meaning that one of the units on the map represents 250,000 feet or inches or meter in reality. And in this type of a small scale map can focus on a larger area, but it's going to give us less detail. A large scale map, again, gets its name from a larger fraction. Here we focus on a small area, but we can also include a lot more detail about what you might see in this type of map. And when we have to create a map to display the shape of a whole country or a whole state, if the state or the country is big, then the way we project it is going to matter because its shape will be affected. The way that the country is displayed is going to be affected. Let's continue briefly through scale. On the first map on the left side, we're looking at metropolitan New York. And here we are zoomed in. You could say we have a small scale map. Compared to the others, we have a smaller fraction of 1 to 10 million. And so we can include more detail about the cities in the metropolitan area of New York. In the medium map, we have the metropolitan tri-state region. So we have a large urban region, and our scale is getting smaller as well. And finally, we have a small scale map on the right. I would say these are all small scale maps, but the smaller the scale, the smaller the fraction, the less detail and the more generalization. So you can also see that our features go from an urban area that is depicted here in the darker tan, darker brown color, to by the time you have less detail, it doesn't make sense to display an urban area, and so we have to generalize our data as well. So as we are mapping between scales and between small scale and large scale maps, issues of how we display our data and how we project our maps are also going to matter quite a bit. So far, if you look at the map that we came out of in Illinois, if you are familiar with the geography of Illinois, you would have noticed that the map that we designed for our first review lab, this map is not projected. It has a no projection, and that's why the state of Illinois looks a bit shorter than it should be. The state of Illinois has a north-south orientation, and it is elongated in this direction, north-south. Here at the bottom, I have chosen a projection for Illinois based on the state plane system. And the state plane the state plane projections are ideal for different parts of the state. However, for a map of a small area like a neighborhood, map projections won't be so important unless you're making detailed measurements. So we will look at what that looks like in our tutorials on the city of Olander. Because we are going to be making some features and maybe offering some measurements, we do need to make sure we know what our projection and our datums are. When we are mapping larger areas, map projection is going to become more important. And so here we can see that we could potentially display the first map without Illinois being projected, but for more accuracy, and so that we don't have all these distortions on the shape of the state, we want to keep the state projected accurately as well. So the projection you choose for larger areas depends on the portrayal of the part of the world that you are mapping. And so here we're sticking with a map that's appropriate, a projection that's appropriate for Illinois. When we are working with thematic maps, remember a thematic map is a map that is not used for navigation. It chooses, it's a map that is focusing on a specific theme. For this type of map, we want to choose what is known as an equal area projection. The reason is that equal areas also affect the way the data appears as it is distributed in space. So for example, when we're mapping the continental United States, when we have a geographic or no projection or plate carré projection, the curvature of the northern United States and its border with Canada is really distorted in the no projection. So we want to use the equal area Albers projection for a thematic map including the whole United States. Hawaii and Alaska also have their customized Albers projection, and the Albers projection is ideal to map the northern latitudes because it's a conic projection. For large-scale reference maps that are used in navigation, the default projection, for example, used by Google Maps is a conformal projection known as the Mercator or Web Mercator projection. And this is ideal for routes and locations because this type of projection preserves angles, right angles at points and intersections. And so this is ideal for navigation because your GPS can tell you left and right since angles are preserved. And so what we're looking at is when we map the continental United States, we would prefer the Albers equal area or a projection that accurately displays the curvature and shape of the United States. If we are focusing on the world, then we have other options. The Mercator is one of the most common, especially for navigation. But if we are if we're creating a thematic map, we could use a different projection for the world as well. Let's look briefly at the Albers equal area. So you can see why this projection would be more ideal for the United States. It's more accurate for northern latitudes. Since it is a conic projection, we pretend that we're putting a cone on the top of the globe, and then we project light from inside to outside. And so we have a few lines where the cone touches the globe, and the area between those lines and where the lines touch, that's the most accurate area. And so we get a map of North America that would include that curvature of the United States that I showed in this map before. The Albers equal area projection also has a length of 1 degree of latitude. Within the Albers equal area projection, 1 degree of latitude equals half the length of 1 degree of longitude, 60 degrees north. So that's closer to the equator. That's closer to the North Pole. And we also have a rectangular grid. A rectangular grid is also often referred to as a graticule. In fact, graticule is the most common name for it. And so projections affect the shape of the geographic area and size layout of the map as well. Let's discuss geographic coordinate systems briefly. Geographic coordinate systems are often referred to as georeferences. These are often a pair of numbers that locate data on a grid. We are most familiar with latitude and longitude. And latitude and longitude derive their georeference types from measuring angles on the Earth, since we consider the Earth a three-dimensional spherical object with 360 degrees around, but also a 90-degree angle. When we measure from the equator to the North or the South Pole, we are able to use what are these angular units. We can also transform these angular units into what we call decimal degrees. And in some cases, depending on the coordinate system that your projection uses, XY coordinates will be displayed as measurements in feet or meters as well. Geographic data can be loaded based on a pair of XY coordinates. You've probably collected some XY points in a GPS or on your phone, and you can see that we have that. That's a geographic feature. It could be a tree, it could be a fire hydrant. There are different types of coordinates. Like I mentioned, we have degrees, minutes, and seconds. So this is a more accurate version of the angular units. We have also decimal degrees, which is a transformed version of DMS. And we also have the UTM system, which works with the Universal Transverse Mercator projection. Coordinates can be converted from one type to another. Our software is able to do that. We don't have to know all the math these days, and so that's where GIS software has become really useful in doing all the mathematical work, heavy lifting in the background as well. And coordinates can cover part or all of the Earth. So one of the advantages of designing this system of georeferencing is that we can have a coordinate for all of the Earth. So the more common one, as I mentioned, is the angular unit that is derived from a prime meridian along 0 degrees of longitude. And we also have the equator, where we derive our latitude points. As I mentioned, we can often display these angular units as degrees, minutes, and seconds, or decimal degrees. To convert latitude and longitude into DMS, you can also follow a simple sort of division by 60, because we are working with these angular units and degrees. Okay. Continuing with our discussion on projections, there are many projections that you're going to come across. The more common are Mercator, Robinson, and there's a new one called the Equal Earth, which we are experimenting more with and which we think is more accurate, or at least visually, it's also more appealing and seems more accurate than others. The Mercator projection, for example, greatly exaggerates the size of Greenland and the size of Antarctica. Compared to Africa, for example, Africa in reality is 15 times larger than Greenland. However, because the Mercator projection distorts the North and the South Pole, this does not. This map shows Greenland and Antarctica as being quite large. So all projections are going to have some sort of distortion. Your job as a geographer, cartographer, or GIS specialist is to make sure that those distortions are pushed off to the sides of the map that you don't need. So if your map needs areas around the equator, then, for example, this would be an okay. If you're mapping areas in the equator, this would be an okay projection to use. We've already talked about coordinates, latitude and longitude. Make sure that you know that oftentimes when we took math and we were looking at grid systems, we often refer to as X, Y, but make sure that you notice that X, Y does not directly translate to lat long. In fact, lat long translates to as YX, okay? So just make sure that you understand that difference there. In geographic information system software like ArcPro, we have two types of coordinate systems recognized by the software. We have geographic coordinate systems and we have projected coordinate systems. The geographic coordinate systems have spherical coordinates in DMS or also in decimal degrees. And a geographic coordinate system measures angles from the Earth's center. We need an ellipsoid and we also need a datum to be able to have our GCS coordinates. A projected coordinate system, at its foundation, it's going to rely on a GCS with its ellipsoid and datum. But the projected coordinate system is specifically designed to transform that three-dimensional object into and project it onto a flat surface. Oftentimes measurements here are going to be in meter or feet from the point of origin. So far in our tutorials for this class, we have only looked at projections and datums briefly. For example, in our tutorial 2-1, when you were creating the feature data set for the geodatabase land records, you needed to specify the coordinate system because all of the features inside this feature data set, in order for them to match the geography, they have to have the same coordinate system, right? So we need to define that. And if you recall, we selected the projected coordinate system for north central Texas because this is where Olander, the city we are working on, is located. So we selected a projected coordinate system that meets local characteristics, for example, north central Texas, and also the units we want are in US feet. Sometimes you will also find them in US meters as well. And so we selected this coordinate system, and later on, once you do that, it's going to apply to your feature data set. And so all of the features that you create or that you digitize inside these feature classes are now going to automatically have this as their GCS and their projected coordinate system, is going to rely on the North American datum of 1983 as well, right? So this is one of the ways that we have looked at it. Don't worry so much about your maps right now and getting the correct projection or datum in Geography 113. I am introducing this subject now, but I will also go more in depth when we cover this, when we cover projections and datums in cartography in Geography 114. Nevertheless, it's still important to understand what's going on in terms of our projections and coordinate systems, because we might want our maps to look a specific way. Okay, so let's look at projections again. When we look at projections, we often say that when we turn that three-dimensional object into a two-dimensional object, we're going to have distortions going from 3D to 2D. Okay, so what are those distortions? We often use the acronym SAD: shape, area, distance, and direction. That could be the shape of a continent or a country, the area that it's displayed, the distance between points, and the direction, north, south, east, or west, could also be distorted. So these are the types of distortions that can happen going from 3D to 2D. In order to get around these issues, we have come up with 4 classes or families of projections. The first 3 are the most common projections. Or rather, they're all common, but there's 3 projections that are known as planar or azimuthal projections. And here we use a flat. We pretend we have a flat piece of paper and we project from the center of the world onto that flat surface. We also have the conic projection, so the Olbers equal area that I talked about. This is a conic projection with a central and meridian and a standard parallel here on the projected from the center of the globe. And so this then gives us this shape that is very common to the Olbers. And we also have cylindrical projections. The cylindrical projection has 3 types, known as the normal projection, in which we wrap a cylinder of paper around the globe and we get the plate carré, or we get the Mercator projection. We also have the transverse, which is very common for the transverse Mercator, which we're going to look at in a minute. And we also have the oblique cylindrical projection, which is a sideways projection as well. The 4th class or family is mathematical. And that one, for example, the Robinson projection is a mathematical projection that relies on algorithms in order to avoid some of these distortions. So classifications of projections are based on the properties that are preserved. So for example, a conformal projection preserves angles and shapes of small areas. So this is the Mercator projection, is a conformal projection, and here we are preserving those angles, especially for the shapes of small areas, and that is why the Mercator is useful for navigation up until the present. We also have the equal area or equivalent projections, so these preserve the relative size of area. The Olvers is one of these projections. We also have equidistant, which preserves distances, and azimuthal, which preserves directions. Let's look at some common projected coordinate systems or some common projections. The universal transverse Mercator is a common one used. When we look at this Mercator projection, the transverse, we want to imagine that there are different bands. Remember that the line at which the cylinder touches the globe is the area with the most accuracy. And so the Mercator, the UTM projection, what it does is basically you create all of these different strips or zones. There are 60 strips for the whole world, and each strip has 6 degrees of longitude wide, and they have this north-south orientation. In the United States, for example, out of the 60 strips, we have 10 zones in the continental United States. So California, as you can see here, if you're mapping Northern California with the UTM system, you would use UTM Zone 10. If you're mapping Southern California, you would use UTM Zone 11. And in the continental United States, we have a total of 10 zones. Because Alaska and Hawaii are in such different, if we look at Alaska, for example, and if we look at Hawaii, they're so far from the continental United States, they have their own UTM zones as well. UTM zones have a north-south orientation. We also use false eastings as well. UTM zone works well with GPS data, and you're going to see UTM used in military and environmental, in military operations, but also environmental operations and uses. And this type of map is ideal for small-scale mapping because there's less distortion along these different 6-degree zones. So UTM coordinates are going to be displayed in meters. As I mentioned, we have UTM zone 11N. Then we also have UTM zone 11 south, right? So we have north zones and south zones. The way that these zones works is you have to find an origin point. The origin for the northern zones is usually 0 degrees at the equator, so 0 degrees north. And the easting is 0 degrees at 500,000 meters west of the original central meridian, right? So this would be, each band has a central meridian, and the origin point is at 500,000 meters west of the central meridian as well. So coordinates here are in eastings relative to an origin, so that origin that we mentioned, 500,000 meters west of the zone of the central meridian, and the northing is relative to the equator. So north is in relation to this meridian, and the northing departs from the equator. So this coordinate, for example, here in Colorado would be easting is 397,800 meters. Its northing is 4,922,900 meters. UTM zones south work slightly different. Coordinates are also, again, eastings relative to an origin, except that the central meridian and the northings are relative to an origin 10,000 meters south of the equator as well. So this is a bit different compared to the UTM zones for the north and for the south. Another common projected coordinate system that we use in the United States is the state plane coordinate system. As the name implies, it is specific for the states of the U.S., and this is commonly used by state organizations or government agencies, county agencies, local city governments, and urban planning as well. The state plane coordinate system is divided by states. In total, we have more than 120 zones. And depending on the shape of the state, we also have different projections for different zones. So for example, states that have an east-west direction use a Lambert conformal conic projection. So for example, in California, we have several east-west shapes. States that have a north-south direction or zones that have a north-south direction use a transverse Mercator projection. So for example, parts of Florida that are north-south, but also New York, outside of Long Island, they use the north-south direction. So here we look at this shape of of New York, West New York, East New York, and West New York, Central, and East New York. They have the transverse Mercator projection, and the Lambert conformal conic projection is used for those east-west orientations. So similarly here in Florida, the Panhandle is also in that Lambert conformal conic, whereas Miami and Tampa areas are north-south direction. One other land partitioning system that you might also run into is the U.S. Land Partitioning Survey, USLPS, often referred to as the Township and Range System. This is a federal system that was created since 1785, and its east-west lines are known as township, its north-south lines are known as range, and this is a much more common system that you're going to find in the East Coast, in the original eastern United States. Cadastral mapping is more common in areas west of the Mississippi, and this is used for boundary surveying, also known as plat mapping. And we also have often a meets and bounds surveying system in which measurements are also identified with bounds and landmarks, and this is also common in the eastern United States. Okay, let's look at the relationship between coordinates projections and datums. So, as you might have heard, cartography is the science or practice of drawing maps. However, underlying all of this, we also have the science of geodesy, which is the science of accurately measuring and understanding the Earth's geometric shape, orientation in space, and gravity field. Geodesy is a branch of mathematics and geography, and geodesists assign coordinates to all points of the Earth. Before 1980, coordinates of points were determined with surveying tools to measure distances, but today, geodesists use the GPS system to measure points of the Earth's surface. So basically today, we rely on satellites for accurate measurements of points on the Earth's surface. So as you might have heard, the Earth is spherical, but it is not a perfect sphere. And it is actually known as an oblate spheroid. And the best way to represent this shape is using an ellipsoid that has a semi-minor and a semi-major axis. This is because since the Earth is not a perfect sphere, it means that there's a part of the Earth along the equator that is going to be wider than its north-south, its axis, right? So we have a minor axis and a major axis. And what this means is that depending on where you want to measure coordinates and points on the Earth, we're going to have different ellipsoidal approximations. The reason why we need different ellipsoids is because since the Earth is quite large, the ellipsoid that might work best in one part of the world might not work well in another part of the world. This is because the Earth is a lumpy, imperfect sphere. And so if we look at this diagram here, the line here without the dash, the solid black line, matches very well with the geoid of the Earth. And we'll look at the geoid in a bit more detail in a minute. Right, but this geoid and this ellipsoid match very well here. But if we follow this ellipsoid to another part of the Earth, then this ellipsoid is not really useful for this other side of the world, right? And so what we're going to need is we're going to need a better local ellipsoid. So this dashed lined ellipsoid matches better with the geoid here. So this is why we have different datums for local datums for small scale mapping. The most common datums that we use in the US or North America are NAD 83, which is an update from NAD 27, and we also have the WGS 84 datum, which has had so WGS 84 is introduced once we have satellite systems as well, and GPS coordinates are usually tied to the WGS 84 datum. So the reason why we have a NAD 83 is because NAD 27 was originally created with surveying, but NAD 27 was with surveying, and NAD 83 is created with satellites. The image that I have here is a model with some exaggeration of the geoid of the Earth. The Earth is kind of like a potato. Its gravity fields are also different in different parts of the world. And this is why we need datums, local datums that work better for specific parts of the Earth, right? So the North American datums, NAD 83 and NAD 27, these are local datums for North America, whereas WGS 84 is an ellipsoid that is generalized for the whole world. So again, when we derive, we have our geoid in this red here, right? And so we have an ellipsoid, the blue ellipsoid, is going to fit better at specific parts depending on the spheroidal height that it has from the geoid. So again, as I've mentioned, the Earth is not flat. It is not a perfect sphere. The Earth is a spheroid, and the geoid is this model of the imperfect Earth. To measure the surface of the Earth would depend on ellipsoids, which are approximations. And datums are used to define the shape and size of the Earth. Datums have a common single point. We also have datums that are local datums versus Earth-centered datum. So for example, NAD 27 is a local datum. It is measured from Meads Ranch in Kansas. NAD uses the WGS 84 satellites. So this would be a centered, Earth-centered datum. Local datums have several components. The first is the spheroid, a datum origin, and benchmarks to identify those locations on the Earth. So again, the North American datum of 1927, and the one of 1983. The NAD 27 is located in Meads, or rather its origin is centered on Meads Ranch, Kansas. Since 1927, the world has changed. We understand that the Earth is a changing system, and so whenever there's an earthquake, whenever there is a volcano eruption, or just erosion also moves the benchmarks and changes where these original benchmarks for the NAD 27 were placed, right? And so in some parts of the country today, relying on NAD 27 means that your data is off by maybe 10 feet or 100 feet in some locations. The further you get away from Kansas, the more your datums are distorted. So NAD 83 gets around this by using satellites for location, and NAD 83 closely approximates the WGS 84. It's, however, only applicable to North America. So surveying, cartography, and land use planning use NAD 27 and NAD 83. WGS 84 is that other very common datum for most of the world. If a country has not updated to having a local datum, for example, most likely they're going to rely on WGS 84, which is geocentrically positioned with respect to the center of the Earth. So this is also an Earth-centered datum where we assume that the origin point is at the center of the Earth. And GPS coordinates that we use today are based on WGS84, which WGS84 again is a global datum and it's an approximation. So it's going to fit generally, but if you want more accuracy, then you would use a local datum. Let's look briefly at the NAT27 and NAT83. So again, explaining that the NAT27 relies on the Clark spheroid of 1866, and its origin point is in Meats Ranch, Kansas, right? Whereas NAT27 relies on the spheroid GRS80 ellipsoid, and so its origin is at the center of the Earth. However, it is still very useful for North America as well. Okay, we're coming to the end of this lecture, but I just want to also mention that sometimes whenever you need to update a system of data, you're going to need a geographic transformation when you need to update projections and datums. Okay, so a geographic transformation is a mathematical operation that converts the coordinates of a point in one geographic coordinate system to the coordinates of the same point in another geographic coordinate system. One of the most common is updating data from NAT27 to WGS84 or NAT83. This can happen, for example, if you are working for a county or a city government and they are digitizing or scanning maps, or they are bringing in shape files that were originally recorded in NAT27, anything that might have used the NAT27 datum. These files are being updated to WGS84, for example, right? So to the new to WGS84, and so for this you would need to use a transformation, which again is one of the tools that comes with our GIS software. We're not going to focus on transformations in this class 113, but we are going to focus on transformations in Geography 114. For now, this has been mostly an introductory lecture on projections, coordinate systems, and datums. So remember that there are many types of projections because there are different ways to display the world. Your projection is going to be much more important if you are using if you're looking at a small scale map to try to display a large area of the world like a country or a whole state. Projections have coordinates as well, or these are georeferences. It's a pair of georeferences to identify a point on the Earth, and we rely on latitude and longitude, which can be displayed as degrees, minutes, and seconds, decimal degrees, or you can also use UTM, which has its own way of displaying coordinates. Coordinate systems come in two types. The geographic coordinate system, which is spherical, and it relies on these on degrees, minutes, and seconds on these spherical units. It measures angles from the Earth's center, and it needs an ellipsoid and a datum. So the projected coordinate system, once you are projecting a map, these already have a GCS, especially the ellipsoid and the datum component. And this is to project, for example, a map to a flat surface. So whenever we're displaying a large area of the world, we want to make sure we use the appropriate projection. And oftentimes we're going to find these in meters or feet from the point of origin. Okay, that's it for this section on projections, coordinate systems, and datums. Make sure to review the lecture and to look up any of these topics if you want to find out more about them. I have already provided some videos in our module to give you a basic introduction, but we will continue to run into these throughout our class, and definitely when we get to Geography 114. Coordinates, projections, and datums are very important because as a person that comes from geography, this is the secret sauce of understanding how our maps are accurate or why our maps might not be accurate or might not be displaying the data where we want them. So it is important to understand that if you're going to do some sort of analysis, then your data has to be lined up with the same datum, for example. Or if you want to display a map accurately, then you have to use the correct projection to do so. And again, this is that secret sauce that we have as geographers, right? That science behind how our maps are or are not accurate, or how our data is or is not accurate. That's it for this lecture. If you have any questions, as always, see me during office hours or send me a message through Canvas, and I will get back to you as soon as possible. Like I said, you can also do some research on any of these topics and send me any questions you have. Have a good week, and I look forward to seeing you in class.